Excellent. Okay, so as I said, we're going to learn, oh, sorry about that. So we're going to talk today about what is a group, right? And this is what we're going to study. The course is like groups and symmetries, but when we say the symmetries portion of that, we actually mean we're studying those symmetries as groups. So there's a very real sense in which this is a course in group theory. And in order to do that, we need to talk about what a group is. Now, I said at the beginning of the year, in Math 102, you learn this lesson about what a field is. And a field is gross, right? Field has like 12 axioms in it. And it's this really big, complicated thing. And I've said to Shai a bunch of times, like, I don't think you should teach fields to 102, right? Like maybe teach them groups, because groups have 3 axioms. And so it's a little bit simpler. It's something you can dig your teeth into. So those 3 axioms, let's do it from the beginning. So a group is a set together with a binary operation, right? And a binary operation, we know, just eats 2 of a thing and produces 1 of it, right? And we've seen plenty of these things before. So for example, addition is a binary operation, right? You give me 2 numbers, I eat them, and then what do? I spit out a new number, which is their sum. Multiplication is a binary operation, right? Take 2 numbers, multiply them, you produce a single number. Function composition is a binary operation, things like this. So binary operation just means that you take 2 numbers or 2 elements and you smush them together somehow to create a new one. And the binary operation basically needs to satisfy 3 things. So 1, it has to be associative. And that's kind of our usual, right? Just that it doesn't matter the order that you do the multiplication in. Like if you want to do AB first and then multiply that by C, that's the same thing as doing BC first and multiplying by A. And maybe it's kind of worth keeping, putting a little note here. So associativity tells us oh, my writing, not great. Let's try that again. So associativity says that we can write down the following thing. So we can write something like ABC, and that's not ambiguous, right? Like because it doesn't matter how we do the bracketing, we'll always get the same answer out. So we can kind of skip the brackets. Skip the brackets, and we're not worried about that. It's well defined no matter what order we actually do that multiplication in. So that's the benefit of associativity, is we don't have to carry around these parentheses everywhere. Okay, so the second axiom is the existence of an identity, right? So basically, when you smush things together with the identity, nothing changes, right? That's the idea there. And we've seen plenty of examples of these sorts of things. So for example, the additive identity. So if our binary operation is addition, then the identity is 0, right? Because we know that if we take 0 and add it to any number, like 7, we just get out the number 7, right? 0 plus 50 is equal to 50. Adding across, like adding to the 0 to the 0 element doesn't do anything. So that's the identity for 0. The identity for multiplication is the number 1, right? Because 1 times 7 is 7, 1 times 50 is 50. So doing multiplication against the number 1 doesn't change anything, right? So that's what the identity is. And then finally, the existence of inverses, right? So for addition, we know that the inverse is the negative number, right? It's the inverse of an element is the thing against which the binary operation of the 2 things together give you the identity. So for addition, the identity is 0. So the inverse is the negative, right? 7 plus negative 7 is 0. And for multiplication, it's the reciprocal, right? 7 times 1 over 7 is equal to 1. For function composition, if this is possible, right, it would be the inverse function, right? So the identity for function composition would be the identity map, which just maps every element to itself. And then for function composition, it would actually be the inverse function, where that makes sense. All right, so hopefully that makes sense. And just with those 3 axioms by themselves, we've got a ton of things that we can do. The theory is very, very rich. So let me give you a couple of examples. So notice as well, maybe I should state this immediately. Note, there's no statement here about commutativity. There is no statement about commutativity. right? i.e., does AB equal BA, right? Does the order in which, like the side in which that you do the binary multiplication, does that matter? And so there isn't this condition. So notably, groups can be non-commutative. And I'll give you an example of that in a second. So groups can be non-commutative. If a group is commutative, then we give it a very special name. We call it an abelian group. So if we add a fourth axiom, for all AB in G, AB is equal to BA. So that's what I mean by commutativity, right? This is the commutativity condition. Commutativity. Then we say that our group is abelian. Then we say that G is abelian. Okay, now I think in the book, abelian is capitalized. I don't tend to capitalize it. And I was kind of saying before, the greatest compliment that you can ever give to a mathematician is to name something after him or her and not actually capitalize it. So abelian is named after the mathematician Abel. And you know, some of us capitalize it, some of us don't. I don't do it. I think the book does. Obviously, that doesn't make a difference, right, in terms of the mathematics. So let's go through a bunch of examples so you can see, you know, some examples of groups. And you know what, I'm going to start with like a really, really easy example. All right, so let's do something like example. Okay, so you've all taken linear algebra, right? I'm pretty sure 224 was a prerequisite, or we were saying maybe you could do 202 instead, but I'm pretty sure you all have some linear algebra in, you know, background. And the vector space, the underlying additive structure of a vector space is always a group. So one, the underlying additive structure, and I'll elaborate what I mean by that. The underlying additive structure of a vector space is always a group. Right? So what I mean by this, now you might say like, well, that's a crappy example. Like, I don't know what those words mean. Why would you do that? So let's make that a little bit more concrete, right? So let's take something like R3, okay? And we know how to add vectors in R3. So I'm just gonna look at addition, okay? Not scalar multiplication. That doesn't make sense. Scalar multiplication is not a binary operator. So that's not what we're gonna look at. We're just gonna look at the addition of vectors in R3. This is definitely, this is a group, right? So let me just kind of write it down so that we're all on the same page. So if I give you two vectors like this, W1, W2, W3, we know how to do this, right? We just do it component-wise, V2 plus W2, V3 plus W3, okay? So this is certainly, it's associative, right? So one, this is associative. This is associative. Let's make some more space here. No, too far. Two, the identity element is what? The identity is the vector. Right, it's the zero vector, right? So the vector of all zeros, like so. And then three, the inverse, we can probably guess. The inverse of V1, V2, V3 is negative V1, negative V2, negative V3, right? It's the negative. Okay. And okay, so that was for R3. But for those of you who have seen abstract vector spaces, you imagine this is always true, right? In an abstract vector space, you always know that addition is associative. It's actually one of the axioms of a vector space. You know that there exists a special vector called the zero vector, which does exactly what the identity is supposed to do. And you know that there always exist additive inverses. In fact, of the like 10 to 12 axioms of a vector space, however many there are, you can find exactly the 3 group axioms show up for the additive structure, right? And this is why one of the things that I say anytime I teach linear algebra is like, there are these 10 axioms. I don't remember what these 10 axioms are for a vector space. This is stupid. This is not how mathematicians think about what a vector space is. Okay, so for a mathematician, I'll tell you what the mathematical definition of a vector space is to a mathematician. Some of these words aren't going to make sense, but you're going to hear the word group and you're going to be like, oh yeah, okay, that makes sense. So a vector space is a ring acting on a group in a compatible way, right? So that's the definition of a vector space. It is a ring acting on a group in a compatible way. And you say, okay, well, like, group, sweet, okay. And the group is the underlying additive structure. You always demand that the addition on a vector space comes from an abelian group. Okay, so this is kind of our first example. You've all had plenty of exposure to this. And like I said, at some point, go pull out your linear algebra notes, pull out that big list of axioms, and see if you can circle exactly which ones are the group axioms in the context of a vector space. Okay, so this is something that you can immediately take. The reason why I bring this up, and I actually, for whatever reason, I don't think this example is in the book, but this is a great place to construct counterexamples. Okay, so this is a really good place to actually build up counterexamples. Okay, let's do another example. And again, if there are any questions, don't hesitate. Don't wait for me to ask questions. Just throw them in the chat or something, and I will see them. So let's give myself some more space here. All right, let's do another example. So one that is classic that we kind of know from 102, Zn, right? The collection of integers modulo n. So define, I'm not going to go too much into detail in this because I think we've seen it before. So we're going to define a relation on Z by saying A is related to B if A is congruent to B mod n, right? We know that, we've played with that. And then the set of equivalence classes is an example of a group. So define Z n as the set of equivalence classes. And we know there are exactly n of them. That's why, it's called Zn. Is a group with, okay, so the identity, or I guess I should tell you how to add elements first. You just kind of do it naively, right? That's kind of, I think, exactly what you'd expect. And 0 is the identity. Okay, now the reading goes into this, so I don't want to, really expand on this. I'll let you check that out in the reading, and hopefully you already have, so you've seen how exactly that works. It's not terribly complicated to actually check. I mean, it's certainly, addition is associative because it's associative in the integers. I've told you what the identity is, and by the definition of this, it clearly is. And then the only thing you really need to check is about the inverses. But again, the inverses is exactly what you would think it would be, right? Negative n is the equivalence class of negative n. Okay, so there's nothing, I think, crazy there. If you want, go through the motions, actually check. Again, this is an example of an abelian group, right? So A plus B is equal to B plus A. Everything works out fine, right? This group is abelian. Is abelian. Okay, so far everything is abelian. I'm going to do one more abelian group and then I'll give you a non-abelian one, okay? Everything's fine so far. Everyone's like, okay, this isn't too crazy, hopefully. Okay, cool. Great. So this one, now I'm not really a big fan of this group, but we can do cool things. So we're going to take what's called the group of units. So we define the group of units. And I'm not sure if that language is actually used in the book. right? So it's Zn star is the way that we denote it. And it's the collection of elements of Zn which are invertible under multiplication. Of Zn, which are invertible under multiplication. Okay, and again, maybe like this is a big class of groups, so let's maybe do an example. So we've got, if we took U, this is why, the book uses the notation U is for units, and units actually means things that are invertible under multiplication. Okay, that's what a unit is. So if we take, for example, U4, so what we want to do is let's look at Z4, right? So over here on the right, I'm going to say, let's look at Z4 star. So as an aside, we know that Z4 is equal to 0, 1, 2, and 3. Okay. And now, so Zn is a group under addition. Basically what we want to do is we want to try and make this now a group under multiplication, but it doesn't work out perfectly because under multiplication, the identity, so with multiplication, the identity is now 1, right, instead of 0. So with multiplication, the identity is now 1. But we run into this issue that if you're not invertible, I mean, being invertible is one of the axioms of being a group, right? So this would be a big problem for us if we had non-invertible elements. So what we're going to do is we're just going to throw away all of the elements that aren't invertible in Zn. And we're going to say, oh, hopefully this thing ends up being a group. And it turns out it is. The proof is a little bit more complicated than Zn, but it is in the reading still. But that's the idea, okay? So we say we want to turn Zn into a group under multiplication. In order to do that, we've still got an identity. We still have associativity. So we need to make sure the existence of inverses. Let's just get rid of everything that isn't an inverse, that doesn't have an inverse. Okay, so what are, under multiplication, the invertible elements of Zn? And again, multiplication just is the way you think it should be, right? When you multiply equivalence classes, you take the equivalence class, the product. So what are the invertible elements in this group? Anyone? So let's go through them one at a time. Is 0 invertible? Is there any equivalence class that I can multiply by 0 to get 1? Ah, right. Okay, so Justin, you almost have it, right? But you included 0, right? So we don't want to include 0. So 0 we're going to throw out. 1 certainly is invertible, right? Because 1 times 1 is equal to 1. Justin, right? You correctly identified 2 is not invertible. And you can just check all the numbers, right? 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 0, 2 times 3 is 2. None of those numbers is equal to 1, right? So 2 is not invertible. 3 is invertible. Somebody tell me, what is the inverse of 3? What do I multiply by 3 to get 1? Exactly, right? So Justin, yeah, exactly. And 9 mod 4 is 1. So 1 and 3 are the only invertible elements. And so they are going to be, they are our group, okay? And again, there's a little bit of work to check here, but in this case, the group only has 2 elements, so it's actually pretty easy to check. Certainly everything here is invertible, it's associative. And the one thing you might want to check is that it's actually closed under the binary operator. So 1 times 3 is 3, 3 times 3 is 1, 1 times 1 is 1. Yeah, everything works out. We don't somehow multiply these two things together and get 7, and then we'd be in a lot of trouble. So everything does actually manage to work out, right? So that's the group of units. Does anyone know a quick way of determining whether an element is in UN, right? So if you look at the elements of Zn, how can you check whether they're an element of UN? What's the trick? I think it is in the reading. So just the question is, do you remember in the reading what it said? Like, what's special about 1 and 3? If they are divisible by n, they aren't in. That's certainly true. And then Sunshao, GCD AB is equal to 1, right? So like that's the condition, and you can see that that includes yours, Justin, but is a little bit, there's a little bit more, right? So you need, and Sunshao, one of those should be n, right? So basically what you need is that if the element is co-prime to n, then it's in your group of units. Okay, so for example, if we wanted to very quickly figure out what U12 is, somebody tell me what are all the numbers between 0 and 12 which are co-prime to 12? So 1 is certainly co-prime. Is 2 co-prime? No, 2 is not co-prime, right? GCD of 2 and 12 is 2. 3 is not co-prime, right? 4 is not co-prime. 5 is co-prime, right? GCD of 5 and 12 is 1. 6 is not. 7, yeah, exactly. Okay, so Paula, you've written them all out for me. Perfect. Right? And so this is like a really fast way to figure out what exactly the group of units are. You just go through all the elements and you say, are they co-prime to n, right? Are they co-prime to n? And if they are, they're in your group of units. Okay, so that's the easiest way to work this out. And again, you can check, like, look, if you multiply any of these things together, you get one of the other things inside of there. It's a little bit tricky, but like 5 times 7 is what? 11, right? 7 times 7 is 1. 11 times 7 is 5, right? So it works out. Okay, does that make sense? Everyone's okay? Okay, hopefully that's all right. Let's do a non-abelian one. So the book, you know, gives you, I think, like matrices as a non-abelian example. I want to do a different one, and we'll come back to the matrices because we know that matrix multiplication is not commutative. So that's kind of a natural place to do it, but I want to do a slightly different one. Okay, so let X be a set. And I want to show you this one early. We are going to come back to this one in later, maybe not next week, but I think maybe the week after. We're going to come back to this one because this is an important one. This is where the symmetries part comes in. So let X be a set and define S sub X to be the set of all bijective maps from X to X. Okay, this is a group. And it is generally non-abelian under function composition. So this is a generally non-abelian group under composition. Okay, and you can check that it satisfies all of the group axioms. So the identity, right? So I said, first of all, the group operation is function composition. Is to do that thing, right? And the identity is the identity map, which just takes X to itself, right? And then the inverse. Now, this is important, right? We know there's inverses Y. Exactly, because it's bijective. Right? Yeah. So we know that bijective maps have inverses. So that's critical, right? We can't take the collection of all maps from X to itself. We have to use the bijective ones because we need to guarantee that their invertibility. And you can, again, imagine, you can see why this is not commutative because we know that function composition is not commutative, right? We know that F compose G is generally a different function than G compose F. Right? So there's no expectation, and 99.999% of the time, this is a non-abelian group, right? With a silly example of like, if X is a single set with a single element in it, you know, there's only one bijection, and so evidently it's the trivial group, so it's commutative. But most of the time, this is a non-abelian group, right? Now, what we're going to study, we're not generally going to study this set for any x. We're actually going to look at specifically finite x. And this is where the word symmetries in the course title comes from. When we talk about groups and symmetries, this is called the symmetric group on X. This is the symmetric group on X. So when we talk about symmetries, that's what we're talking about. Okay, that's where that word comes from. Now, let's do a more concrete example, right? Because again, this is a whole class of examples for every possible set, whether X is the real numbers, the complex numbers, some set of sets, whatever the case is. This is always a group, but we can go and we can be a little bit more concrete. So let's do something like the following. So let's take something like, so more concretely, let's let n hat be the set 1, 2, all the way through n. And in an abusive notation, we'll often write, we just write Sn for Sn hat, right? So i.e. it's the collection of all bijections on the set 1 all the way through n. Okay, so it's just the bijections of those things. And again, I want to make it even more concrete. Let's work in S3. So let's say, looking at S3, so what I'm going to do is I'm going to define the following bijection. So define sigma. We often use sigma when we're talking about symmetric elements. So this is going to be the map from 1, 2, 3 onto 1, 2, 3. And I'm going to say sigma of 1 is equal to 2, sigma of 2 is equal to 1. No, so let's say 3. And sigma of 3 is equal to 1. Okay? And hopefully you agree that's a bijection, right? It's injective, it's certainly surjective, it's definitely bijective, right? And you can see exactly what the inverse would be, right? You would take 2 to 1, 3 to 2, and 1 to 3, right? So it's relatively easy to construct its inverse. Now, notationally, this is quite a quagmire. There are a bunch of different ways of writing these things down. And we're actually going to see a really great one in a couple of weeks. But just for us right now, here's a great way that a lot of people will write this down. We often write that kind of like in this weird shape. And the way that you would read this is you read it from top to bottom. So if you look at this, what this says is that sigma of 2 is equal to 3, right? So 2 goes to 3. So along the top, you'll always just have the numbers in order, 1, 2, 3. And then underneath, you'll say what each of those things maps to, right? So 1 will map to 2, 2 will map to 3, and 3 will map to 1, right? And the reason why this is super convenient is because you can now do things like compute sigma composed with sigma. Oops, maybe let me go stay consistent and be yellow. So sigma compose sigma. So let me kind of write that out like this. 1 maps to 2, 2 maps to 3, 3 maps to 1. Let me show you why this notation is useful. Okay. So what I'm going to do is I want to figure out what 1 maps to, right? So I'm going to say, all right, well, 1 maps to 2. And then I'm going to come over to here and say, oh, well, 2 maps to 3. So that means that in total, as I follow through all of the paths, 1 has to map to 3. Does that make sense? Do you see how I did that? Right? So starting on the right, because we know that function composition, right, moves right to left. I said 1 maps to 2, and then I moved to the thing on the left and said, well, 2 map to 3. And so therefore the full composition 1 maps to 3. Okay, and if that makes sense, finish this before I even get a chance to do it, all right? So figure out what does 2 map to and what does 3 map to, right? But if there are any questions, don't hesitate to ask me that. This isn't necessarily the notation we're going to use in a couple of weeks, but it is a frequent notation and it is useful for being able to do this, okay? So let me finish it. Hopefully you got ahead of me and managed to figure it out for yourself. 2 maps to 3, 3 maps to 1. And in fact, once you've got n minus one of them, you know what the last thing has to be. Okay, does that make sense? Everyone's okay? Hopefully that's fine. And then you can check on your own sigma compose sigma is the identity element. Okay, so notably, eventually you compose them enough, you get back to the identity. And that's a useful thing. And we're going to talk about what that is in a second. Now, let me show you that this is truly non-abelian. Okay, let's create a different element here. Okay, so maybe let's define something called tau, and I'm going to let tau be the map 1, 2, 2, 1, 3, 3. Okay, so tau switches 1 and 2, but leaves 3 the same, right? And then I'm just let me rewrite down what sigma is, just so that we have it in front of us. 1, 2, 2, 3, 3, 1. All right, so let's compute what sigma tau and tau sigma are. Okay, and again, don't even wait for me. Just jump ahead if you think you can do it. It's good practice. Okay, so 1 maps to 2 maps to 1. 2 maps to 3, and so 3 must map to 2. And then tau sigma. Oh, shoot, did I do them backwards? Yeah, sorry, that's tau sigma is the one above here. Tau sigma. And then, so this one I want to be sigma tau. So 1, 2, 3, 2, 3, 1. 1, 2, 3, 2, 1, 3. 1 maps to 2. 2 maps. Right? So tau sigma does not equal sigma tau. Okay. So I'm going to pause here, give you all a second to catch up if you're writing down, just to make sure everyone's on the same page. Again, don't hesitate, though, to ask if you have any questions about what's going on there, because we need to be comfortable with these things. Again, this isn't our primary area of focus right now, but this is an important group that we are going to come back to a lot later. So it kind of makes sense to understand how exactly these things work. Okay, so this is non-abelian, right? Tau sigma is not equal to sigma tau. Okay, now I'm going to move on. Hopefully, again, if there are any questions and you're busy typing them, don't hesitate. Keep on going. Let me know if there are any issues there. So there's lots of examples, and there are a bunch of examples that I didn't even do, right? So for example, there are you can talk about matrix groups, things along these lines. And we'll come back. I'll bring these up as examples, so don't feel as though you've missed something out there. But I want to transition a bit, because if we just did examples of groups, I could go all day. Like, we're not even talking about dihedral groups, right? Which are an important sort of group that we're going to talk about. But those ones are a little bit more complicated to define. So I really am going to relegate that to a couple of weeks from now. And the next thing I want to do is I want to talk about the order of a group. Okay. So the order of a group is the number of elements in the group. So if it's a finite group and it has, 7 elements in it, then that group, the order of the group is 7. All right. So that's not too bad. The order of a group is its cardinality. But for our purposes in this class, we're often not too concerned whether the group is countable or uncountable. It's just either it's finite or it's infinite, right? Those are kind of the two categories that we're going to be talking about. And then the order of an element is the number of times that you have to act on it with the binary operator, like act on it with itself, before you get back the identity. Okay. And if no matter how many times you compose something with itself, you never get back to the identity, then you would say that that element has infinite order. Okay. Now, as an important kind of point here, for abelian groups, we often write the order a little bit different. And I think notationally, the book is fairly consistent in only using this multiplicative notation, right? So G, 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 dot, 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 G. If we do that n times, right, that's G to the power of n. But in the case of abelian groups, we often don't use the multiplicative notation. We often use the additive notation where we do something like G plus G plus G plus dot, dot, dot plus G. And we'll do that n times. And that would be NG, right? And so this is kind of annoying because, you know, whether we're using multiplicative notation or additive notation, you know, actually is going to change what the order of a group is. Or it doesn't change what the order of a group is, but it changes whether the n is in the exponent or whether it's, you know, this multiplicative factor in front. So that's unfortunately a little bit annoying, but just kind of keep that in mind. So when we write things multiplicatively, we take powers of G, and when we add them additively, we take multiples of G. Okay, so the order is the smallest n such that this is equal to the identity. Okay, and if no such n exists, then we say that its order is infinite. Exactly, exactly. So yeah, great example. From above here, maybe let me just kind of say that explicitly. So for sigma in S3 above, the order of sigma was equal to 3, right? No, exactly it was. Let me scroll up so we can see it again, okay? And don't worry, I'll come back. So here's where we did that computation, and we see, okay, sigma itself is not the identity, right? In fact, the only element whose order is equal to 1 is the identity, right? Because everything else, if you're not the identity, then your order just can't be 1, right? Now, when I compute sigma squared, right, this thing here, this is our sigma squared. Okay, that's not the identity either. And then when I compute sigma cubed, I did get the identity. So 3 was the smallest number here, such that sigma was equal to the identity, right? Does that make sense? So the order of sigma in this case is equal to 3. Okay, hopefully that makes sense. Now, somebody, can you tell me what was the order of S3? How many bijections are there from a set of 3 elements to itself? Like, so from the 3 element set to the 3 element set, how many bijections are there? Exactly, there are 3 factorial. Right? So again, you might have to remember how your counting arguments go, but basically the idea is 1, 2, 3, and then you've got the set 1, 2, 3. So let's figure out where 1 maps to. Well, how many options do you have for that? Well, you've got 3 of them, right? And now, when you figure out where 2 maps to, you've only got 2 options because it has to be a bijection. So you can't map it back to the thing that you chose for 1. So now you only have 2 options. And then once you get to 3, you only have 1 option. So every single time you decrease the number of options that you have, and that results in you getting n factorial, right? So 3 options for 1, you have 2 options for 2, you've got 1 option for 3, and generally the order of Sn is n factorial. Right? Okay, so you can see this group gets really, really big, really, really fast, right? The symmetric group on 10 elements has a little over 1 million things in it. But yeah, okay, here's another cool thing that's interesting. Again, this describes bijections. So, well, actually, you know what? Maybe I should save this conversation until we get to subgroups. But okay, somebody remind me to come back here and talk about Rubik's cubes. Okay, but like Rubik's cubes are groups and they're related to the symmetric group. Okay, so we'll want to come back to that pretty quickly. So that's the order of elements. Okay, and there's definitely a question now, right? One of your assignment questions, question 4, asking you about the order of elements, and that the order of elements is generally badly behaved, right? That's what that exercise question is doing. It's a wonderful question, and it says, you know, even though the absolute value behaves nicely with real numbers, the order of an element does not behave nicely. When you multiply things, you have no idea what their order is. Okay. So what I want to do here is let's maybe compute some orders. Okay. Oh, actually, you know what? Here's a really good exercise. So exercise. And I want you all to try this. So exercise. So find the orders. So both, let me make sure I get the correct groups here. Right, so both U5 and U12 have order 4. Okay, right, we checked that, right? So you can check U5, well, 5 is prime, so you know, the set of elements in here are just 1, 2, 3, 4. I'm not going to write the brackets. 1, 2, 3, 4. And then we said before U12 is what? 1, 5, 7, and 11. Okay. So what I want you to do is to compute the order of each of these elements. Okay. And I'm going to give you a couple of minutes to do it. So compute the orders of all of these elements in their respective groups. Okay. And from this, I want you to conclude that these groups are different. Okay. So, you know, hint, you're obviously going to get different orders for one group than for the other. And if they were the same group, they would have to have, all the elements would need to have the same orders, right? If there's some way of like, if one group was just the other one, but in disguise, all the orders, you would have to have the same number of order 1 elements, order 2 elements, order 3, order 4, et cetera, et cetera, et cetera. So compute the orders of these elements and see what you get. And I'm going to give you like 5 minutes to do it. And then I'll take it up myself. And then that'll probably be a good time for us to take a little bit of a break. All right. So give that a shot. I'm going to give you 5 minutes. Okay. So, you know, the chat brings up a good point, which is the way the groups of units are defined, it's kind of easy to lose track of what the binary operation actually is, right? So keep in mind in UN, the binary operation is multiplication mod n, right? So in U5, we're going to multiply these elements together, and then we're going to compute what they are mod n. But because we're computing order, we're just going to take basically powers of 2, powers of 3, powers of 4, mod 5 on the left-hand side, and then powers of 5, powers of 7, powers of 11, mod 12 on the right-hand side. So let's start with the left-hand side. Let's start with U5. Okay, so for U5, okay, the order of 1 is 1, right? 1 to the power of 1 is equal to 1, no problem. So we've got the order of 1 is equal to 1, certainly true. Now, let's start computing powers of 2, and then we're going to stop when we reach the number 1. And if we eventually get into this cycle where we can never reach 1, right? Let's say the pattern starts to repeat itself, then we would know that the order is infinite. So we've got 2 to the 1 is certainly equal to 2. 2 squared is equal to 4. 2 cubed is what? That's 8 mod 5, so that's 3, right? 2 to the power 4 is 6, and that is equal to 1, right? So the order of 2 is equal to 4. Is that okay? Does everyone kind of see how that worked? I want to make sure there aren't any issues there, right? We're computing multiplication mod 5 in this case. Okay, so we're trying to figure out what is the least power I need to raise things to get the number 1 out. So if we do 3, so 3 to the 1 is equal to 3. Obviously, that doesn't work. We knew that. 3 squared, so that's 9 mod 5. So that's 4 again, right? 3 cubed is 12 mod 5, so that should be 2. And then 3 to the 4 is equal to 1. Okay, so the order of 3 is equal to 4 as well. Okay, and then for 4, we get 4 to the 1 is equal to 4, and 4 squared is 16. So that is 1. And so the order of 4 is equal to 2. Okay, did everyone get that as well? Hopefully I'm not alone. If you think I made a mistake, please don't hesitate to tell me, because I can make mistakes too, right? I'm not infallible, but does that look right? Maybe let me write the order of 1 over here. Be a little bit more consistent with my presentation. Okay, awesome. Great. So now let's do U12. And U12, I think, is actually a little bit easier, right? Even though the numbers are a bit grosser, like we can multiply the numbers, you know, they're not too bad. So for U12, all right, we still get 1 to the power of 1 is equal to 1. So certainly, you know, the order of 1 is equal to 1. Okay, what is it? So 5 to the 1 is 5. 5 squared is 25. Mod 12 is 1. Okay, so the order 5 is 2, right? As soon as it is equal to its own inverse. The order of 7, so 7 to the 1 is 1, or sorry, is 7, and 7 squared is 49. The nearest multiple of 12 is 48, so this is again equal to 1. And then 11 to the 1 is 11. 11 squared is 121. Nearest multiple of 12 is 120. So this is again equal to 1. All right. So again, I think hopefully it's clear here. These are different groups, right? Because in U12, every non-identity element was its own inverse, right? Everything had order 2. But in U5, you had a bunch of these elements that actually had order 4 in them, right? So they were like, these must be different groups of order 4. So that's interesting. So there are at least 2 groups of order 4. Now, here's a cool thing. We don't have the ability to prove this yet, but these are all of them, okay? These 2 groups are the only 2 groups of order 4. Now, here's an interesting question for you. You can probably think of another group of order 4, though, right? What's another group of order 4 that you're just like, for sure, this is a group of order 4? Can anyone think of one? Z4, exactly. We know that the additive group Z4 is also a group of order 4, right? So Z4 must be one of these, right? And now the question is like, what does that mean? What does it mean for Z4 to be secretly one of these? So maybe what you should try doing is computing the orders of elements in Z4 and see, do they match up with U12 or do they match up with U5? And that would be a good hint to you that those 2 things are secretly the same group. And this is going to lead us to the notion of homomorphisms and group isomorphisms. Okay, so this is a little bit further down the line, but just like we have, you know, when we talk about linear algebra, we have this notion of, you know, vector space isomorphisms. And a vector space isomorphism is saying these 2 vector spaces are the same. They just might look a little bit different. We're going to have group isomorphisms, which say that these 2 groups are the same, even though they might look different. So one of these groups is Z4. And an interesting little problem for you is to try and figure out which one of these things is Z4. And the easiest way to do that is probably to compute the orders of the elements in Z4 and figure out which of these 2 it is. Okay. And that only works because I've told you, you have to take this on faith, but it only works because I've told you that these are the only 2 groups of order 4, right? So, you know, take that for what it's worth. Normally this wouldn't work. For example, there are a lot of groups of order 24, right? Okay, so let's take a 10-minute break there. It is 2:07 by my clock. So I'm going to come back at 2:17. Let's take a 10-minute break starting pretty much now. When we come back, we'll talk about subgroups. And then from that, we'll talk about centralizers, normalizers, and the center and these sorts of things. Okay, I'm going to go camera off, refill my coffee and stuff. But again, if you have questions, throw them in the chat and I'll be happy to answer them. Okay, so I'll see you all in 10 minutes. All right, everyone, so we're going to start here again. Now let's see. So, you know, in the lecture slides that Ali has posted, he doesn't talk about subgroups at all, which I think is weird because subgroups are clearly like an important part of this section. So I am going to tangent into subgroups a little bit. And I'm going to try and make it clear by drawing the analogy of subgroups with vector subspaces. Okay, and hopefully that will help you understand what exactly they are and why these conditions that we impose end up working. And again, as I kind of said, like the fact that we know that there's always a group living inside of a vector space suggests that, you know, there's a close relationship between vector subspaces and group subspaces. You know, it's not a perfect analogy, but there's a lot of similarities between the two of them. So we can hopefully, if you have a good understanding of vector subspaces, hopefully we can use that intuition to help guide, you know, how subgroups work. Okay, so, you know, recall, so definition. You know what? I usually use red for definition. So let's do that. So definition, right? If G is a group, then a subset H of G is said to be a subgroup. Be a subgroup of G if it is also a group under the same binary operation. If it is also a group under the same binary operator as G. Okay. So, and this is a common thing that we talk about in mathematics. We'll talk about something in general, for example, vector spaces or a group, and then we talk about sub-vector spaces or subgroups, which are, again, just examples of vector spaces that live inside of a bigger vector space, or groups which live inside of a bigger group. Okay, it's the same sort of idea. And so, you know, if you want, you could like draw something like a subgroup. You could be like, oh, okay, here's G, right? And let's highlight the identity element, okay, because we know that it's a very distinguished and special element. And then whatever the subgroup is, so it's some subset that lives inside and is also a group. And so immediately what we conclude is that because it's a group with the same binary operator, they actually have to share the identity, right? So the identity for any subgroup right must be the same as the identity of G. Right? And again, that's not crazy at all. Like, if you think again about subspaces, right? What's the distinguished element of a subspace? Well, it's the zero vector, right? And for spaces, we know that the zero vector also has to be in that subspace. And so we have the same sort of thing here, right? We have this distinguished identity element, and any subgroup must also contain that element. Is there always going to be only one identity? This is a great question, Hongwei, actually. You can prove, you know, outside of the context of subgroups, we don't need subgroups to do this at all. You can prove that if the identity exists, then it's always unique, that there's one and only one identity. The proof isn't too bad. I can't remember whether it's in the book or not, but it's a good little exercise to play around with some of the group axioms. So you can prove that the identity is always unique, and so that therefore there is only one of them. Yeah, exactly. The inverse is also unique. Is it because it wouldn't be a well-defined operation if not? For what, the uniqueness of the identity? Like you can just, I don't think there's any issue with well-definedness of the binary operator, because what you would have is you would still have distinct inputs potentially mapping to the same output. So that's not necessarily an issue with well-definedness, but it's just something you can directly prove. And the way that you prove it is you say, suppose that I have this other thing which also acts like the identity, and then use the properties of the identity to show that it actually had to be equal to the original identity. Or the equivalent proof, which is almost the exact same, as you say, suppose that I have this different element which acts as the identity, and then show that it actually is equal to the original identity, and that's a contradiction. But it ends up being like, it's a one-line proof. It has like, 2 or 3 equals signs in it. It's a very straightforward, very quick proof. It's worth doing, right? So for any of you who haven't proven it yet, I recommend that you just give it a shot and make sure that you can. So it is a great question. There is only one identity. And then the lesson to take from this part is that that identity element has to be shared by every subgroup, right? So there could be other subgroups as well, right? So we could have another subgroup in here, and maybe it's this weirdly shaped thing, and maybe it even kind of intersects with H a little bit. Maybe let's call that K. It has to have the same identity element as well, okay? Now, when we learned about subspaces, right, when we take linear algebra, we learn what is it that you need to prove that a space is a subspace, right? You want to check, right? So when we learn linear algebra, right? Often I think they don't define subspaces, and you can all tell me depending on how you learned what a subspace is, but they often define it as the following, right? So they say, W is a subspace of V if the following 3 things are true: the 0 vector is in W, and then W is closed under addition and scalar multiplication, right? So if W1, W2 are in W, then W1 plus W2 is in W. Is this how subspaces were defined for you? Right, this was actually the definition, right? If C is in your field, which often was R, so let's just use R, and W is in W, then CW is in W, right? That's, I think for many of you, that was actually the definition of a subspace. And that's wrong, okay? That's like, it turns out to be equivalent, but that's actually not true. So the definition of a vector subspace is, again, it is a subset of the original vector space that is itself a vector space under the same notion of addition and scalar multiplication. Oh no. Yeah, okay. So it's gonna be a little bit loud here, just give me a sec. Okay, but the idea is, a subspace is just a smaller vector space living inside the original vector space. Okay, that's the idea. Just as we defined a subgroup as being a group that lived inside of the bigger group, or a smaller group that lived inside of the bigger group. Okay, yeah, hold on. We just have to hold on a second here because there's about to be a fire alarm test. So unfortunately, just give me like a minute or two. Okay, I think the fire alarm test, it's not a real fire. The fire alarm test has gotten quiet enough. They just, blare it out for a little bit and then it goes to the background. But hopefully, so I did some writing in the meantime. So what I want to say here, and sorry if I'm kind of like repeating it because I don't honestly remember what I was saying. When you learn what the definition of a vector subspace is, what it should be is a smaller vector space living inside the big one. Okay, now it turns out if you prove these 3 things, right, that 0 is in the subspace, it's closed under addition, and it's closed under scalar multiplication, those 3 things alone are enough to prove that this subset W is in fact a vector space, right? You don't have to reprove all 11 axioms or whatever they are, because most of them are automatically true because W inherits them from V. Right? So if that makes sense, these are the 3 that you need to prove in order to, like, they're the only things that really could go wrong. Now for a group, this is actually how like I learned the definition of a subgroup, not that it was a little group, but that it satisfied these three properties. But it's the same sort of idea, right? Like if you know that these three properties are true, you can prove that H is a group, right? You can prove that it is a group with under the same binary operation as G. And for example, we don't have to prove that scalar or that the group multiplication is associative, because H would inherit that from G. You assume they have the same binary operator, right? So if you, so associativity of the binary operator in H automatically is implied because the operation is associative in G. And if you're not comfortable with that argument, you need to think it through a little bit and then like post on Piazza or something if that doesn't make sense, because that is something that's going to save you a lot of time of being able to say, listen, this obviously has to be true because these elements are also in G and the multiplication is associative there. Okay. So we see, hopefully you can see this like kind of direct analog behind what we say about vector subspaces and what we say about subgroups. Now for subgroups, there's also this nice criteria, which is proved in the notes. And so I'm going to restate it here because I'm probably going to use it a fair bit, but let me kind of restate this. So it's going to be a theorem, and I'm going to put it in green. So theorem, a subset H of a group G is a subgroup if and only if, whenever you give me two elements of H, so if and only if for every AB in H, AB inverse is in H. Okay. Is number two the composition of H1 to H2? It's whatever the group binary operator is. So that is just whatever the group operator is, right? So if it's additive, if it was an abelian group, I'd probably write it as H1 plus H2. If they were functions, I'd write it as H1 compose H2. Usually though, when we're lazy and we're talking about abstract groups, we often just use the multiplication operator, and we usually just write that as concatenation. So that's just what I mean there. Yeah. Okay. So this is a nice criteria, this thing in green here, because it gives you an ability to check whether or not you're a subgroup just by checking this one condition, right? I'm not going to prove this. The proof is in the notes, but if you can check that if you take me any two elements in H, then AB inverse is in H, then you're guaranteed it's a subgroup. Now that doesn't mean that this thing on the top right-hand corner is not useful. I actually still prove that most things are groups using that, but that is a thing that you can do. Just the existence of the inverse in H is enough. It depends on what you mean, right? So in the sense that like this condition has a bunch of stuff built into it. This condition has effectively that the group is closed under your binary operator and that the inverse exists, right? This condition kind of has both of these things built into it, right? So closure of the operator. And containment of inverses. Right, because you can imagine if the identity, yeah, exactly, it's like everything else. And Tima, yeah, absolutely, it's like the AX plus B for vectors. You're right, that's actually a really great example and analogy for the vector spaces, right? Is it has kind of everything built into it. So it's a nice kind of shorthand way of doing it. But like I said, I definitely still use the thing that I have in the top right-hand corner there. I use that plenty. And there often isn't necessarily a lot of shortcut or you don't save a lot of time by using the green thing versus the yellow thing. It doesn't make a big difference. But of course, it helps to have different tools in your toolbox, right? Because sometimes the green thing will be easier and sometimes the yellow thing will be easier. So if you just kind of have all of these, rolling around in your head, you're probably okay. And if you only have one rolling around in your head, that's probably okay as well, right? You can do anything with the yellow definition. Okay, let me see. What did I want to do? Let's do a little exercise here. Okay, here. Let's do a concrete example of a subgroup. And again, there's plenty of subgroups. For example, when we were talking about the symmetric group, if you're dealing with a symmetric group on 5 letters, you can imagine that the symmetric group on 3 things is like naturally a subset of that, right? Or is naturally a subgroup of that. So, kind of keep that in mind. I guess I should, you know what, actually, it just occurred to me too. I haven't shown you the notation. You'll have seen in the notes. Just let me make a little note here about notation. So notationally, we know that this means subset, right? That means subset, but not every subset of a group is going to be a subgroup, right? So that means subset. Now the notes use this curly thing. I don't even know if I can draw it because I don't use it a lot. So it uses that for subgroup. A lot of people actually just use the less than or equal to sign. Okay. And if you use a less than or equal to sign, like less than or equal to sign, everyone will know what you're talking about. Okay. So if you don't make your thing kind of curly like it is in the book, you're probably okay. You can just use the less than or equal to sign and it's completely clear what you mean, right? Lots of people use that to mean subgroup and it's totally okay. So you can use that as well. And that's how I'm going to do it as well. In my notes, I'm not going to try and write this curly thing. It's not going to work out well. So I'm just going to use the less than or equal to sign. All right, let's do an example and actually see something concrete. So let's say like, I'm going to make this an exercise and I'm going to give you a couple of minutes to try it out. It's really not too bad. So exercise, show that this thing this is a very important example. Is a subgroup of GL2C. Okay, so the notes, for example, would have told you what GL2C is, right? GL2C, maybe just let me remind you of what GL2C is. So it's the collection of all invertible matrices, 2x2 matrices, right? So it's the collection of all matrices, 2x2 matrices with complex coefficients such that the determinant of A is not 0. Right, so they're the invertible 2x2 complex matrices. So I'm going to give you this thing here. Maybe let's give this a name. Let's call this H. There's this thing here, which are the upper triangular matrices. So what I want you to show is that the upper triangular matrices and the invertible upper triangular matrices are a subgroup. Okay, so I'm going to give you a couple of minutes to do this. You can use either the green theorem that we had above or the yellow theorem. They're about the same amount of work. They don't make a big difference, but give that a shot. Okay, so hopefully you've had an opportunity to try that one. This actually is one where I think, so in my mind, if I were to do this, I wouldn't almost do anything. I'd say, look, by the yellow definition, this is clearly a subgroup, right? And again, this is what I would do. I wouldn't say don't do this on a test. I would say the identity element is clearly in here, right? A setting the diagonal to be 1 and B to be 0. That's clearly an element of the upper triangular matrices. So it contains the identity. I know that the product of 2 upper triangular matrices is still upper triangular. I think that's like a pretty common linear algebra fact that we've learned. So I'm closed under multiplication. And then, yeah, okay, the only thing I kind of have to do is convince myself that the inverse of this thing is also an upper triangular matrix, but that's not too hard to do. And in fact, you need that if you use the green theorem anyway, right? You have to find what the inverse is. Nonetheless, if we actually wanted to write all of this out, those 3 steps take a fair amount of work. So I think in this case, the green theorem is actually going to be the easiest way. So that's how I'm going to do it, because I'm lazy and I want to do the least amount of work possible, right? So we're going to recall, hopefully you remember this formula. So recall that the inverse of AB0D is 1 over the determinant, right? Which in this case is just AD. That's why AD can't be 0 of D negative B 0A. Okay, hopefully you remember that from linear algebra, that we have this kind of slick little formula that allows us to, just in the 2x2 case, right, set up this inverse. And yeah, okay, great. We can already see that the inverse of a upper triangular matrix is upper triangular, right? So we kind of, like I said, we needed that regardless of how we were going to prove it was a subgroup. But now at this point, all we have to do if we want to check that it's a subgroup is we need to show that A, B inverse is an element of the group. And so we could do something like, okay, take A1, B1, 0, D1, comma, A2, B2, 0, D2 to be in our subgroup. And then let's show that A1, the first thing times the inverse of the second thing, is also an element, is still also upper triangular, right? That's effectively what we're doing. So A1, B1, 0, D1. And we're going to do matrix multiplication with 1 over A2, D2. Sounds like a Star Wars character. D2, negative B2, 0, A2 like this. And 1 over A2, D2. We know that's not 0, so there's no issue there. A1, D2. That's it. 0. And then oops. Let me just erase that. B1, A2 minus A1, B2. And then A2, D1, right? Which is indeed upper triangular. So that's an element in H, and we're done. All right, so that's, for example, how you would use that green theorem that we had above. Again, though, I'd recommend try proving it using the 3 conditions just as extra practice. Show that it has the identity, show that it's closed under multiplication, and then show that the inverses exist. And you can see here that like this also encapsulates most of that proof, right? It very much, the product of 2 upper triangular matrices is going to look very similar to this. And, as part of this, that very first line is the statement that the inverse matrix is also upper triangular. So, the proofs are almost identical in terms of length. But if you want to do it for extra practice, go crazy. So that's a subgroup. All right. We're going to come to centralize later. I do want to spend a little bit more time talking about subgroups. Let's do. Okay, here's an exercise that isn't too bad. I think you can all hopefully get this one pretty quick. So let G be a group, an abelian group. Let G be an abelian group. And fix some natural number. Show that this thing, G to the power of n, okay, does this prove the identity exists too? So Hongwei, the interesting thing is, if that identity always holds, you can prove from the identity that AB inverse being an H implies the identity is an H, right? Here, let me just go up. So this fact being true, note that if I multiply, if I did A1, B1, 0, D1, and then multiplied it by its inverse, then that would also be an element of H. And so that would prove that the identity is actually an H as well, right? But that's the whole point of the green theorem, is that you don't have to even worry about the identity, because if you prove that condition is generically true, it has the identity built into it, right? It's that cool little thing that it has so many parts built into it. Okay, so show that G to the n is a subgroup of G. Okay, so again, I want you to think about what exactly this is saying. So I've fixed some natural number n, let's say the number 3. And what I'm going to do is I'm going to take every element in my group and exponentiate it to 3. Right? So I've got G1 cubed, G2 cubed, G3 cubed, G4 cubed, etc. So I take the power of 3 of every element of the group, and my claim is that this is also a subgroup. Okay? When n is equal to 1, you obviously get back the original group, but when n is equal to 2, you probably get a strict subgroup, right? So give this a shot. This is not a difficult proof, but so give it a shot and kind of see how that works out. I'm going to give you a couple minutes to try that. Okay, so I didn't give you too long. I probably only gave you 3 minutes or so. And I think that this is probably a question that looks maybe intimidating, but is surprisingly not, right? Like if you just start doing it, you're like, okay, this isn't terrible. I'm going to do it using the yellow theorem that we had before. You can definitely do this one using the green theorem, but let me do it using the yellow one, just so that we have, variety is the spice of life. So first things first, the identity is definitely in here because if you take the identity to the nth power, it's still the identity, right? So note that e to the n is equal to e, which is an element of g to the n. So it contains the identity element, right? Maybe let me put a 1 in front of there because that was the first thing. Number 2 is we want to show, this is actually the hardest one. We want to show that the product is closed under the group operation. So we want to show that if we take 2 elements in g to the n, their product is also in g to the n, right? So let's let a and b be in g to the n so that a is little g to the n and b is h to the n for some g and h in normal g. And again, we want to show that their product is in here as well, right? Now, a times b is g to the n h to the n. That's gh to the n. Why? Because that's not normally true, right? But what very important thing guarantees I could actually do that here? Exactly, the fact that it's abelian, right? Normally gh to the n is gh, 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 but the fact that it's abelian means that I can group all the g's together and all the h's together. So here we use the abelian. Okay, so that ended up being important. And this is clearly something, right? GH is an element of big G. So this is something to the power of n, and that's exactly what we needed it to be, right? So we're good there. And then 3, if a equals g to the n is an element of capital G to the n, then a inverse is equal to g inverse to the power of n, which is also an element of h, right? Just if you look like a power of n, you're an element of h. So that's what we're saying. So you can see that one isn't too bad. And so we're done, right? Because we've proven the 3 things. If you use the AB inverse condition, then you kind of ultimately have to make like the statement of 2 comes in again, but now with the inverse, like 2 and 3 end up getting smushed together as a like little lemma that you have to do before you can do the AB inverse, and then AB inverse is trivial. But nonetheless, it ends up being basically the same amount of work. So, I'm not too worried about it. If you did it this way, I suggest that you give the AB inverse a shot just as practice. And then if you did it that way already, phenomenal, right? Like you've already tried that. So I've got a bunch of other exercises for subgroups, but I do want to try and get this centralizer, normalizer stuff out of the way. And then if you really want, like I have office hours right after this too, so we can talk about it. You can drop into the office hours. We have a conversation about it. Or if there are questions as well on Thursday, we can bring it up. I'm more than happy to talk about it. But okay, so we've got these 3 definitions here. The book actually has a 4th one, the normalizer, which we're not going to, I guess, worry about too much until a little bit later. But we've got the center of the group. Center is super important, okay? So the center is very important. It's the set of all things which commute with everything, right? They're the elements of the group which commute with everything else. And generally the center is not terribly big, right? You can imagine that if you're in an abelian group, the center of the group is, the group. But if you're in a non-abelian group, the center is often very, very small. So that's the center. The centralizer is very similar, but it is the set of all elements which commute with only your element A, right? So the centralizer, in fact, the book proves this nice fact, which is that the center is the intersection of all of the centralizers. And I claim that that is in some sense evident, right? Because if CGA is the set of all elements which commute with A, then when you take the intersection, you get the set of all elements which commute with everything. And that should obviously be the center, right? But again, think about that if you're not clear and make sure you can prove that one from scratch. That's a nice result. And then the final thing is the centralizer of a subgroup which is the set of all things which commute with that subgroup, okay? So the exercise that I want to do today is the following, and I guess maybe I'll just prove it because we don't have a lot of time left, but right, is the following claim, which is that for every subgroup H of G, the center of G is a subgroup of the centralizer of H is a subgroup of H. Okay. So like I said, I think I'll just do this. I wanted to give you time to do it, but we've only got 5 minutes left. So I think that maybe I should just do it. So we already know that the center is a subgroup. And of course, if you want, like, if you really want to try this one, you should just leave the lecture now and then check the recording later. Like, don't let me ruin this for you, right? Like if this is something you want to try on your own. So we already know that the center is a subgroup, right? That's in the book. So I don't think it needs to be reproven. You can check the proof there. It's nice. It's not terribly hard. And if you haven't checked the book, try and do it yourself because this isn't a difficult proof. Now I claim that for any subgroup H, ZG is a subset of CGH, right? Okay, I'm not claiming subgroup yet. We should check subgroup. But again, this is evident, right? If Z is an element of the center, then it commutes with everything. For all G and G. So in particular, it commutes with everything in H. Because if you commute with everything in the group, you certainly commute with everything in that subgroup, right? With everything in H. So Z is in CGH. Okay, so that's not what the exercise wanted us to do, though. It wanted us to show that the center is actually a subgroup of the centralizer. But to do that now, all we have to do is prove that the centralizer is a subgroup of G. Sorry, this should be G. This should not be H. I don't know why I put that there. Sorry. Okay. So let's prove that the centralizer of H is a subgroup. Now we prove that CGH is a subgroup of G. And let's see, how did I want to do this? Yeah, you could do this either way. I actually think, I think the easiest way is definitely actually going to be the yellow. Again, they're basically the same amount of work. So one is the identity in there. Yeah, certainly. Right? E is in CGH since EH equals H equals HE for every element of the subgroup, right? So definitely the identity always commutes with everything. So it also always commutes with everything in the subgroup. 2. Okay, so if A and B are in CGH, then let's write out. Again, if you don't remember, like if you're having trouble doing these proofs, right, make sure that you actually write down what you know. Sorry, that should be B. Right, so we've taken A and B to be in the centralizer. That means that A commutes with everything in H and B commutes with everything in H. Now we want to show that their product is also an element of the centralizer, i.e. we need to show, so we want to show that AB is in CGH, i.e. that ABH is HAB for all H and H. But hopefully you see, like, yeah, that's definitely going to work since ABH, if I bracket that like this, that's A times HB. That's AHB, which is HAB. And that's what we wanted, right? Basically, because A and B commute with everything in H, you can just kind of keep pushing the H through, right? You can just keep taking it to the left. I personally don't think you need to include all these brackets, but I'm doing it just to kind of show you the logistics of how that works. But if you just wanted to write ABH is equal to AHB is equal to HAB, I'd say that's totally fine, right? So AB is in. I keep wanting to make that a G. I don't know why. CGH. Okay, and then finally, if you want to show that the inverse is in there, so let A be an element of CGH. Okay, and again, we know that means it commutes with everything. So in particular then, so that means that AH inverse is equal to H inverse A for all H in H. And you might be like, well, why are you using the inverse here? Like, first of all, it doesn't matter whether you use H or H inverse. As you exhaust every element of the subgroup H, you're going to get every single element. And then the benefit of doing this is now taking inverses. Right? So we're going to get H A inverse is A inverse H for all H and H. Right? So A inverse is in C, G, H. And you might have to think about that one a little bit, like why this and this, right? These are the same thing. Okay, make sure that you think about that and are convinced that, like, yeah, it doesn't matter whether you use H or H inverse. As you let H go over every single element of the group, or of the subgroup H, you'll pick up everything, right? So these two statements are equivalent. If one of these statements is true, the other statement is automatically true as well. Okay, so that shows that the centralizer of a subgroup is in fact a subgroup and gives us the result that we wanted. All right, so are there any questions about that? Okay, if not, then I think we're good there. I'm going to stop the